Welcome back, everyone. Today, we're going to be taking a deep dive into the Open-Sora Plan.
Okay,
It's an open source project
interesting.
that has the ambitious goal of creating a video generation model that rivals OpenAI's Sora.
Wow.
And we're going to be using their technical report, opensoraplan.pdf, as our guide.
Great.
This project is causing a real stir in the AI world, and we're going to unpack why that is.
One of the things that makes open source so exciting is that it's focused on generating high-resolution, long-duration videos.
Yeah.
And that's something that has been notoriously difficult to achieve.
Hmm.
Their approach, which is outlined in the report, is built on three key innovations.
Okay.
A novel variational autoencoder that they call the Wavelet-Flow VAE,
Okay.
a powerful denoising component that leverages both image and video data,
Interesting.
and a set of ingenious control mechanisms that allow for fine-grained manipulation of the output.
Wow. Okay, so let's start with this Wavelet-Flow VAE, or WFVAE as they call it.
Yeah.
I was struck by the fact that they chose to work in the frequency domain using wavelet transforms.
Mm-hmm.
Why is that such a big deal?
Well, traditional VAEs often struggle with the sheer volume of data involved in video.
Right.
By using wavelet transforms, the WFVAE can efficiently break down the video into its various frequency components, making
Right.
it much easier to process.
I see.
The report, specifically Section 2.1, describes how they further enhance this efficiency by introducing a causal cache method.
Okay.
This method allows the model to process the video in manageable chunks without sacrificing the quality or losing crucial information from previous segments,
Yeah.
a must-have for handling long videos.
And looking at the results in Table 6,
Yes.
it's clear that this approach is paying off.
Uh-huh.
The WFVAE outperforms other VAEs in terms of speed and memory usage, while still delivering excellent reconstruction quality.
Mm-hmm.
They even provide a visual comparison in Figure 15,
Right.
showing how well the WFVAE preserves details even in complex scenes. It's like they've found a way to make video data much more manageable for these AI models.
That's a great way to put it.
Yeah.
They've really focused on optimizing the WFVAE, ensuring it's not just a theoretical improvement, but a practical solution for handling real-world video data.
Yeah.
Now, this efficiently compressed representation from the WFVAE is then fed into the next stage, the Joint Image-Video Skiparse Denoiser.
Okay.
As the name suggests, this is where the actual video generation magic happens. It takes that compressed representation and uses a diffusion model to gradually refine it into a coherent and visually appealing video.
The report, especially Figure 4, highlights the complexity of this denoiser.
Yeah,
It's clearly dealing with an immense amount of information.
right.
One of the things that caught my eye was their use of skiparse attention.
Okay,
It sounds like a really smart way to manage the computational demands of this denoising process.
absolutely. Skiparse attention, explained in Section 2.2.1, allows the model to selectively focus on the most important parts of the video, reducing the computational burden without significantly impacting accuracy.
Interesting.
They achieve this by cleverly alternating between two types of skip operations, as depicted in Figure 5,
Gotcha.
to measure the effectiveness of skiparse attention against other attention mechanisms.
Yeah.
They even introduced a new quantitative measure called average attention distance, or ADAVG.
And if we look at Table 1 and Table 2,
Yeah,
it seems like skiparse attention really hits the sweet spot between efficiency and performance. But this Denoiser isn't just about generating random videos. It's about generating videos that respond to specific instructions or conditions, right?
that's where the conditional controllers come in,
Okay.
described in Section 2.3.
All right.
The report details two primary types: image conditional controllers and structure condition controllers.
Gotcha.
These controllers offer incredible control over the generated videos.
The image condition controller discussed in Section 2.3.1 seems particularly versatile.
Yeah.
They describe how it can turn a single image into a video, seamlessly transition between videos, or even continue an existing video.
It's quite remarkable.
Yeah, it is.
What's fascinating is that they frame these tasks as an in-painting problem, as you can see in Figure 7.
Right.
They treat the missing parts of the video as areas to be filled in, using the provided image as guidance.
I see.
The different mask types shown in Figure 9 demonstrate how this works, controlling which parts of the video are retained and which are generated.
The examples in Figure 19 really showcase the level of control they've achieved with this approach.
Right.
And then there's the structure condition controller, covered in section 2.3.2,
Yes.
which uses structural signals like canny edges, depth maps, or even simple sketches to influence the video. It's like giving the model a stylistic blueprint to follow, as visualized in Figure 13.
And they've managed to design this controller to be incredibly efficient.
Wow.
As described in the report, it integrates seamlessly with the denoiser, adding very little computational overhead. It allows for a level of granular control over individual frames that is quite impressive.
Yeah.
So we have this powerful WFVAE compressing the video data, a sophisticated denoiser generating the content, and these controllers adding a layer of fine-grained control. But that's not all.
Oh.
The report also introduces a set of assistant strategies that further refine the process.
Let's dive into those.
Okay.
What are these strategies all about?
These strategies described in Section 3 focus on making the training process more efficient and robust. The first one they discuss is the min-max token strategy outlined in Section 3.1.
Right.
This is a brilliant way to handle videos of varying resolutions and durations.
Okay.
Instead of resizing or padding, which can lead to information loss or inefficiencies, they use a specific formula detailed in Equation 20 to determine the optimal token set for a given set of resolution.
So it's about finding that sweet spot that maximizes data utilization while minimizing computational overhead.
Precisely. Then they introduce the adaptive gradient clipping strategy in Section 3.2.
Okay.
Training these massive models can be unpredictable, with sudden spikes in the loss function that can derail the entire process. Figure 10 provides a clear example of these problematic spikes.
Those spikes look like they could really throw a wrench in the works.
Exactly.
Yeah.
To mitigate these issues, they've developed an adaptive clipping method that uses exponential moving averages, or EMAs, to detect and address these spikes.
Okay.
Figure 11 illustrates how it works in practice.
All right.
They identify outlier gradients and either eliminate them or scale them down, ensuring a smoother training process.
It's like a safety net that keeps the training on track.
Yeah.
Finally, they discuss the prompt refiner in Section 3.3,
Yes.
which seems to bridge the gap between the dense captions used during training and the simpler prompts that users might provide.
The idea here is to utilize a large language model, or LLM, to essentially translate those shorter prompts into more detailed descriptions.
That the denoiser can effectively utilize.
Right, Chuck.
They even fine-tuned the LLM, as mentioned in the training details of Section 3.3, using a dataset specifically designed to enrich the descriptions with information about actions, scenes, lighting, and atmosphere.
Figure 14 really highlights the impact of this refiner.
Yeah.
You see improvements across various metrics, particularly in human action generation and spatial relationship depiction.
It seems like they've really thought of everything to maximize the model's capabilities.
But what about the data itself?
Right.
You can't build a powerful video generation model without a high-quality data set.
You're absolutely right.
Yeah.
They dedicate a significant portion of the report, Section 4, to describing their data curation pipeline.
Okay.
This pipeline outlines a comprehensive set of steps for filtering and annotating the vast amounts of data they're using to train the model.
It's interesting that they've pulled data from such a variety of sources as detailed in Table 4.
They've combined image datasets like SAM, AnyText, and a curated subset of images featuring people with video datasets like Panda70M, Violol, and even stock footage from sites like Mixkit and Pexels.
It's quite a diverse mix.
Is a very diverse mix.
And that diversity is key. They recognize the importance of having a dataset that represents a wide range of scenarios, actions, and visual styles. Their filtering strategy described in Section 4.2 is also incredibly thorough. They've implemented steps to detect jump cuts, filter out videos with excessive motion or low aesthetic scores, crop out unwanted text using OCR, and even assess the technical quality of the videos.
So they've really gone through all these different checks to make sure that the data is really high quality.
Table 5 provides a great overview of these steps and their impact on the final data set.
It's fascinating to see the level of detail they've gone into to ensure data quality. It's not just about quantity. It's about making sure the data is truly representative and conducive to generating high-quality videos. Then, of course, there's the data annotation process detailed in Section 4.3.
And for this, they've turned to LLMs once again. These LLMs are trained to generate detailed captions that describe the content of the videos, adding a layer of semantic richness that the model can learn from.
Yeah.
It's a brilliant way to automate what would otherwise be an incredibly time-consuming manual process.
The data statistics they provide in section 4.4 are quite insightful.
Yeah.
Figure 12 shows the distribution of aesthetic scores, resolutions, and video durations for their different data sets, giving us a glimpse into the sheer scope and variety of the data they're working with.
So they've built this remarkable model, curated a massive and high-quality data set.
So what happens next?
That's where we get to see the fruits of their labor.
Oh.
Let's delve into the results.
All right, let's jump in and see how this Open-Sora plan performs.
Yeah.
Section 5.1 of the report dives into the evaluation of the Wavelet-Flow VAE, comparing it against other leading VAEs in the field. They've really done their due diligence here.
Absolutely.
When did they?
They've used a range of metrics to assess the quality of reconstruction, including PSNR, LPIPS, SIM, and RFVD.
Wow.
These metrics capture different aspects, from the preservation of detail to the smoothness of temporal flow, providing a comprehensive view of how well the VAE performs.
Right.
Their findings on the WebVid10M dataset are summarized in Table 6.
Looking at those results, it's clear that the WFVAE is a top performer.
Yeah.
It consistently outperforms other VAEs, often by a significant margin.
Yeah.
It's not just faster and more efficient, but it also produces higher quality reconstructions.
Right.
And to really drive the point home,
they've
included a qualitative comparison in Figure 15, showcasing the WFVAE's ability to reconstruct scenes with intricate details and motion blur exceptionally well.
They also conducted an interesting analysis of the impact of blockwise inference, detailed in Table 7.
Right.
This technique, which processes video in smaller chunks, can boost efficiency, but sometimes at the cost of quality.
Right.
Their findings highlight how their causal cache method, described back in Section 2.1, effectively mitigates this potential quality loss by allowing the model to retain information from previous chunks, maintaining consistency and coherence, especially in those longer videos.
Now, I know we're all eager to see what this model can do when it comes to text-to-video generation, which is covered in Section 5.2 of the report. They've utilized established benchmarks like VBench and Chronomagic Bench 150 to evaluate the quality of the generated videos. VBench breaks down video generation quality into several dimensions, while Chronomagic Bench focuses specifically on the realism of motion.
These benchmarks, while not perfect, do a decent job of capturing the key elements of video quality, allowing for objective comparisons between different models. And based on their findings, the Open-Sora plan performs admirably.
It's doing pretty well.
Table 8 presents comparison with other state-of-the-art models. And Open-Sora clearly holds its own, demonstrating particular strengths in aesthetic quality, smoothness, and scene restoration fidelity.
And let's not forget the impact of their prompt refiner, which we discussed earlier. It acts like a behind-the-scenes editor, polishing the generated videos and further enhancing their quality.
Precisely.
It's a testament to their thoughtful approach to leveraging the power of LLMs for improved results.
Now, moving beyond text-to-video generation, let's explore the exciting capabilities of the conditional controllers. The image-to-video generation, showcased in Section 5.3, is particularly impressive.
Yeah, it does sound pretty cool.
You provide the model with a single image and a text prompt, and it generates a video that brings that image to life.
The showcase examples in Figure 19 really highlight the potential here. The generated videos are not only realistic and dynamic, but also adhere to the provided text prompts.
They've even included a comparison to other image-to-video methods in Figure 18. And the Open-Sora plan stands out in this comparison.
So it's doing better than some of the other methods.
It does a phenomenal job of incorporating the essence of the input image while still following the guidance of the text prompt.
Interesting.
The other methods either lose the connection to the original image or struggle to generate smooth and coherent motion.
I see.
It's a clear demonstration of the flexibility and control offered by their in-painting approach, blurring the lines between real and generated content, and opening up a world of creative possibilities.
Then there's the structured video generation, detailed in the Section 5.4, which uses structural signals like canny edges, depth maps, or sketches to guide the video creation process. This approach seems tailor-made for creative applications.
Absolutely.
Figure 13 provides some captivating examples
Yeah.
of how these structural signals can be used to generate videos with specific visual styles or effects.
It's like providing the model with an artistic blueprint while still allowing it the freedom to express itself creatively.
The level of control they've achieved without sacrificing quality or coherence is truly remarkable.
It is.
It pushes the boundaries of what's possible with video generation.
And to wrap up their exploration of the model's capabilities, they delve into the impact of the prompt refiner.
Okay.
The ablation studies presented in Figure 14 provide compelling evidence for its effectiveness.
Those studies clearly show that the prompt refiner makes a substantial difference in the quality of the generated videos. We see improvements across a variety of metrics, especially when it comes to action, accuracy, object description, and scenery generation.
They even highlight the refiner's ability to handle multilingual input.
It's interesting.
Making it even more versatile and user-friendly.
It's a testament to their focus on the entire user experience.
Yeah.
They're not just building a powerful model.
Right.
They're making it accessible and intuitive to use.
But even with all these impressive achievements, they acknowledge that there's still room for improvement, and they outline those limitations in Section 6 of the report.
Let's explore those limitations and their plans for future work.
Sure.
In the final part of our deep dive, let's wrap up our look into the Open-Sora Plan by going over the limitations they've identified and what they plan to explore in the future.
They start by talking about the Wavelet-Flow VAE in Section 6.1.
Okay.
And point out that their current decoder design, based on the work of Rombach et al., 2022a, is a bit bulky.
Okay.
It has more parameters than the encoder, which they believe is unnecessary.
So they're saying there's room to make the WF-VAE more efficient.
Exactly.
Without hurting its performance.
Yeah. They're going for even greater efficiency.
That makes sense.
Which is a logical step when you think about the huge scale of video data.
Right.
Next, they move on to the Transformer Denoiser in Section 6.2.
Right.
And it's interesting because even though their 2B model in version 1.3.0 is showing some really good results, they've noticed it has some limitations.
Okay.
Especially in how it understands complex physical interactions.
Yeah, they give examples like a cup overflowing with milk or a car moving forward or a person walking.
Right.
It seems like sometimes the model has trouble capturing how things really move and interact in the real world.
Right. And they have a couple of ideas about why that might be.
Good.
First, they think that the joint training of images and videos, while it's generally effective, might need some tweaking.
Okay.
They mention other models like Open-Sora v1.2, EasyAnimate v4, and Vicatect 2.0, which inherited weights from pre-trained image models and seem to be better at generating high-quality video.
So maybe if they start with a really good image model as a foundation and then bring in the video data, they could get better results.
That's one of the things they're considering.
Interesting.
We're also thinking about experimenting with different ratios of image and video data during the joint training process.
Okay.
Another thought is that maybe the model just needs to be bigger.
So a larger model might be better at understanding physics.
Yeah, as we've seen with CogVideo-X, scaling up the model size seems to lead to improvements in how well it understands physical laws.
But of course, training those huge models comes with its own set of challenges.
For sure. The report talks about some of those technical hurdles. They mention things like deep speed, FSDP 03, mind speed, and Megatron LM, which are all tools meant to handle the distributed training of really large models.
So they're getting ready to train some seriously big models.
It sounds like it.
That's exciting.
They also talk about looking into using a supervised loss during training.
Okay.
That would involve using techniques like flow matching to give the model more direct feedback.
I see.
Which could help make the training more stable.
So it's all about making the training as efficient and effective as possible.
Exactly. They're really trying to push the limits of what's possible.
Aside from making the model bigger and refining the training, they also have some interesting ideas for trying out new architectures and improving how they evaluate the results.
Right.
Let's talk about those a bit more.
In Section 6.2, they specifically mention that they want to look into more efficient architectures.
Okay.
So while Skiparse Attention is already pretty good in that regard, it seems like the benefits are even more noticeable at higher resolutions. They're looking for ways to make it even more efficient during the pre-training phase.
Right.
Which is usually done with lower resolution videos.
So this is about squeezing as much performance as possible from the hardware.
Right.
They're also considering adding more parallelization techniques.
Yeah. Their current model, Open-Sora Plan v1.3.0, only uses data parallelism.
Okay.
They're looking into other options like sequence parallelization, which could make training much faster.
It's all about taking advantage of the computing power they have.
Exactly.
And of course, there's the challenge of evaluation.
Right.
Benchmarks like VBench and Quantomagic Bench are helpful.
But they recognize that human judgment is still the best way to figure out how good a video really is.
I agree, human evaluation is subjective.
It is.
But it picks up on things that those automatic metrics miss.
Yeah.
But it's expensive, and it takes a lot of time.
Right. One of their goals for the future is to come up with better and more reliable automated metrics. Ones that can accurately assess the things that make a video good.
It's something everyone in this field is trying to solve.
Yeah.
As these models get more sophisticated and the videos more realistic, it gets harder to tell the difference between real and generated content.
It does blur the line.
It's fascinating to see all these developments happening.
It really is.
And finally, in section 6.3, they wrap up their discussion about future work by highlighting limitations of their current dataset. They say that their dataset is large and diverse, but it still has some gaps.
Yeah.
Especially when it comes to the types of actions and scenarios.
They did a manual analysis of 2,000 videos from Panda 7DM and found that most of them are just conversations.
Okay.
With not much action or movement.
So it seems like that limited scope affects how well the model can create certain kinds of scenes.
Yeah, they want to expand the data set to include more actions, complex interactions, camera movements, and different video styles.
They also talk about needing higher resolution videos.
Right.
720p is okay for some uses, but it's not enough if they want to create photorealistic videos with lots of fine detail.
It seems like they're in it for the long haul.
Yeah.
They don't want to just build a model that does well on the current benchmarks.
Right.
They're trying to build a model that can generate videos that are basically indistinguishable from reality.
It's ambitious.
It is.
But they seem to have the talent, the resources, and the motivation to make it happen.
It's really inspiring to see a team pushing the boundaries like that.
And the fact that they're sharing their work openly is really valuable for the research community.
Yeah.
And anyone who wants to explore what's possible with video generation.
It's a great example of how open source projects can drive innovation in AI.
Well, that wraps up our deep dive into the Open-Sora Plan.
It was a good one.
An early stage project, but it has the potential to completely change how we make and experience video content.
It's definitely a project to keep an eye on.
The progress they've made in things like VAE technology, denoising, conditional control, and data curation are all big contributions.
Yeah.
And because they're open sourcing it,
Right.
others can build on what they've done and push things even further. Who knows what kind of amazing videos we'll be making in the near future?
The possibilities are endless.
It's an exciting time to be exploring AI-powered video generation.
It really is.
Thanks for joining us on this deep dive.
Of course.
We'll be back soon with another fascinating look into the world of cutting-edge research.
Sounds good.
Until then, keep exploring.